Having considered the graphical perspective on constrained optimization, we now move to the formulaic or the algebra side of things. What we're interested in, again, is finding the highest or lowest values of some function f of xy, max or min, subject to some other combination of x and y being equal to some number. So some equation restricting x and y. And the points that are going to give us these optimums are the ones where the gradient of f is equal to the gradient of g with a scalar multiplier. So a scalar multiplier here. And if two vectors are the same except with a scalar multiplier, that's the same thing as saying the gradient of f is parallel to the gradient of g. So that's going to be our one source of equations, and the other one is simply the constraint itself. So we're going to look for all the x and y's that satisfy this equation and also which satisfy the constraint we were given. The place we're going to go next is once we have the x and y's that satisfy these equations, we're going to evaluate the function at all the points, and guess what? The biggest one is the maximum, and the smallest f value corresponds to the minimum of our function. So this is going to be straightforward. In practice, here's how we're going to work it out. When we're looking at the gradient of f, remember the gradient of f is just a package, the x partial derivative and the y partial derivative for a two-variable function. And so if we want that to be equal to lambda times gradient of g, and gradient of g is another package of partial derivatives, the x and y, then what we're going to get is the x derivative of f is going to equal lambda times the x derivative of g. So we have a nice package there, again with a scalar. And likewise, y and lambda and g of y are going to make another equation. And if you look carefully, there are three unknowns here, x, y, and lambda, and fortunately, we have three equations. So it's quite likely that we'll be able to find a solution to this if we try. We can of course generalize this to three or more variables. We just add one more variable, but we'll also have one more partial derivative to compare, and so we'll get one more unknown and one more equation. So what we're going to do is set these equations up and solve for them. Notice, this is not the unconstrained optimization we had before. The optimum for constrained optimizations are rarely, almost never in fact, rarely critical points. Why are critical points not what we're looking for here? Again, just think of a quick contour diagram. Here's a surface, and we have different heights, and maybe we have a peak, oops, 10, 20, 30, and maybe we get a peak after a bit. That would indicate that there's some maximum in the center of that constrained region, in the center of that contour line, and that's great. So there would be a local max here if we were allowed to go anywhere we want. So if we had an unconstrained problem, this would be where we would look. But in most constrained problems, we might be limiting ourselves to, say, this line here. If that's our constraint, then we can't get to the critical point. And usually these constraints don't go through a critical point. They tend to be off to the side somewhere. And so we end up with a different kind of problem. If we're looking for the optimum along this line, we would go and try to find the point on this line where the contours reach a peak. That's not going to be at what we've seen already as an unconstrained optimization problem, or unconstrained optimization point. It's going to be somewhere along the constrained line, and so we get a slightly different kind of equation. Instead of setting the derivatives equal to 0, we set the derivatives equal to something very specific. So it's still related to derivatives, but not quite as simple as it was when we had unconstrained optimization.